We continue our discussion of orbits in this module by examining low Earth orbits. The map shown is a somewhat out-of-date representation of global surface weather stations on Earth. As expected, land masses are generally much more thoroughly observed than oceans, where calibrated observations are generally only collected on islands, like out here in the Pacific. Weather balloons are only regularly launched from land as well. Thus, the majority of Earth is not well represented by direct observations. And this is what motivates the use of remote sensing in the first place, to fill in these observational gaps. An example of a low Earth orbit is shown here. It usually has a high inclination that allows it to pass over high latitudes and low latitudes. Contrast this with the geostationary orbit that has zero inclination. Geostationary orbiters provide fantastic temporal resolution, but lack in spatial resolution and latitudinal coverage. Constellations of low Earth orbit satellites, on the other hand, can provide data with high spatial resolution and at high or low latitudes. A few terms are important to understand when discussing low Earth orbits and data from satellites in such orbit. Since low Earth orbit is roughly around the poles, a satellite moves from south to north in either the western or eastern hemisphere, and then from north to south in the other. The south to north track is called the ascending orbit, and the north to south track, in this image on the back side of the Earth, is called the descending orbit. A Sun-synchronous orbit is one with a particular inclination, about 98 degrees, that causes the solar angle, or the angle in the sky where the Sun is located relative to a viewer on Earth, to be about the same each time the satellite passes the equator, which is shown by the dashed black line up here. Such an orbit is in retrograde, meaning that the longitude of the subsatellite point drifts westward with successive orbits. The solar angle is determined by the equatorial crossing time, which roughly describes the local time, again based on the solar angle, that the satellite passes over the equator. This is typically designed to be between 10 a.m. and 2 p.m. in one hemisphere. If a satellite orbit is designed to be moving northward over the equator at 10:30 a.m., for example, then we would say that the orbit is daytime ascending with a 10:30 a.m. equatorial crossing time. A sun-synchronous orbit allows for direct comparison of observations collected in different parts of Earth because the solar angle is approximately the same at each longitude observed. Not all low Earth orbiting satellites are in sun-synchronous orbit, however. A high inclination orbit allows for nearly complete global coverage. However, some satellite platforms are designed with lower inclination if their missions do not involve observations of the poles. For example, the Tropical Rainfall Measurement Mission was at a 35-degree inclination and viewed only the subtropics and tropics. The replacement for TRMM, the Global Precipitation Measurement Core Observatory, has an inclination of 65 degrees and can view higher latitudes than TRMM could. Since these orbits are not sun-synchronous, they can make observations of locations at different times of the day. An example of a sun-synchronous orbit is that of the Aqua satellite. An example of 4.5 successive orbits is shown at bottom. It has a daytime descending orbit with an equatorial crossing time of 1:30 p.m. The exact track is repeated every 16 days. And just to sort of track out the orbit, it might do something like follow this red line that my mouse cursor is following, come down, comes out the other end over here, and follows this orbit, comes down, and then the next orbit over, and so on and so forth. Satellites in low Earth orbit have limited field of view compared to geostationary satellites. In this figure, the satellite might only see the atmosphere and surface within the two outer yellow dashed lines, as just an example, with the center dashed line representing the sub-satellite point, this line right here. This means that the data is collected in these swaths. An example of the swaths is shown in a day's worth of data shown right here. There are gaps in coverage at the poles, right up here, the North Pole, and you can see a little bit of a hint at the South Pole, because the satellite does not orbit directly over the pole. There are also gaps in the data near the equator. The swath width for most instruments is usually too small for the field of view in successive orbits to overlap. So the subsatellite point for one orbit might be right here, and then the swath width extends this far. The next time that the satellite orbits is a little bit further to the west, it's centered right here, and that same swath width leaves a little bit of gap between two successive orbits. Similar gaps at the equator can be seen in these examples of MODIS imagery from the Aqua and Terra satellites. Aqua has a daytime ascending orbit, going like this, while Terra has a nighttime ascending orbit, so during the daytime, passing the equator, it's descending, such like this. The two collectively then overlap in coverage over the course of a day, but they have scenes at different angles. They view the scenes at different angles. Satellite orbits can also be organized into constellations. The A-Train is an example of one such constellation of low Earth orbiting satellites. As of 2020, the A-Train consists of 4 satellites that are able to provide observations of aerosol, clouds, radiative fluxes, and atmospheric aerodynamic profiles. And this is the A-Train right here at the top of this figure. They are all in Sun-synchronous orbit at an altitude of 705 kilometers, and they pass over the same point on Earth within minutes of each other. And this allows the provision of comprehensive measurements of several different atmospheric variables coincident in space and time. The C-Train, which orbits at a lower altitude, consists of 2 active sensors, CloudSat and Calypso, which used to be members of the A-Train. You can see the gap where they used to be. They've been moved to a lower orbit in preparation for their eventual re-entry into Earth's atmosphere at the end of the lives of each platform. The C-Train orbits at a lower altitude and therefore moves at a slightly faster velocity, so these no longer give you coincidental observations with the A-Train. However, they do overlap every 20 days or so. We will see some of the data from these 2 satellites, CloudSat and Calypso, near the end of the course. To start out the rest of the course, we'll discuss geostationary satellite data in the next series of modules.